contextuality that
Hi, good day, everyone. Today's seminar will be presented by Som Kanjilal. He has a diverse interest now in quantum information foundation topic ranging from Cheshire cat, weak measurement to contextuality and random access codes. And he has done his PhD with Professor Dipankar Home at Bose Institute. Now he is a postdoc at INL, Portugal. Today, he will be talking about introduction to Sheaf theoretical formulation of contextuality. So, please continue.
uh, so sorry, Sauradev, I started before. So yeah, anyway, as I was saying, so I'll give a introduction to what is sheaf theory and how it generalizes the Fine's theorem to arbitrary compatibility structures. But before that, I've been studying like the sheaf theory is a part of something called algebraic geometry, and I've been and this is the version of math that has been arised in the last century, and it's very difficult for me to. It was very difficult for me to understand this. The learning curve was very steep. I couldn't get the intuition. For a non-mathematician like me, it was very tough to get the intuition of all these things. But uh, what happened is the last year I started to read the autobiography of Grothendieck. And there, Grothendieck basically explained, like Grothendieck is the one who actually introduced this algebraic geometry, sheaf, and all that thing in the mathematics. In that autobiography, Grothendieck explained what he did, like what mathematics he did for mortals like us, and why he quit the mathematics community. But second part is not important. The first part, like just reading about what what is like what need why do we need sheaf theory and what is this whole business of algebraic geometry is about from the perspective of Grothendieck, like finally gave me a little bit confidence to talk about these things. So yeah, so I'll I'll give help me build an intuition. So I hope to give you the intuition. I hope to present that intuition to you here because I won't go to the proofs of the Abramsky-Vandenberg theorem. I'll just try to build the intuition through different examples like Bell, Hardy, Z, Cauchy-Spec, the 18 vector proof if I have time, and then like like what's the intuition behind the shape to give an idea of what the intuition behind the shape. I'll for the first part I'll just copy and paste some passages from the biography of Grothendieck and explain some mathematical terminologies like what is category and what is functor. That's all we need. So you can interrupt me at any time and ask. Okay. So yeah. So now I'll start. So yeah, the idea is that uh, maths. So I'll just say something like I'll just give enough time for you to read the whole passage. So the idea is that you know when you have the arithmetic aspect of maths that deals with the discrete aggregates, you have the analytic aspect of maths that deals with the continuous variation, which we discuss in topological spaces. And before 19th century, we did not, we only had the, we could study the arithmetic properties or the combinatorial properties separately and the analytic properties like shape, sizes, position, these things separately. There was no common viewpoint, as Grothendieck would say, be- that studies both of them together. And we didn't need to because we had Euclidean geometry there. But slowly the non-Euclidean geometries like affine geometry, projective geometry, these arises and it feels that okay, we need some common viewpoint. So the need for common viewpoint also emerged when we found out that okay, we can add geometry like as you probably saw in the earlier chapter, we have the arithmetic and one spectrum which deals with discrete stuff and analytic. analysis that deals with continuous variation and geometry that lies somewhere in between. Like some parts of then in in the beginning of 19th century, 20th century, sorry, we found out that there are geometries that are fundamentally discrete in nature, but still could follow the properties of the topological spaces. If it so these some nice properties of continuous variables, but it is fundamentally discrete in nature in the sense that for each prime we have a geometry in the continuous analog geometry in the characteristics P. So this idea gave us a intuition of changing, this idea gives a notion of how to change. Like we need to change our concept of topological spaces, the continuous variation in such a way that we can allow fundamental discrete stuff and still retain some kind of continuity stuff. So that takes that takes place like we. So what we needed was to understand the space itself, but without understand the space itself. In a way, we want to modify the algebra. We want to find the algebraic structure of the space. We only retain the algebraic structure of the space without the all the topological, without the analytic part. So what happened is that we found some topological invariants that could capture the spaces. These Beatty numbers are basically defined in terms of simplicial complexes, which basically, yeah, that's defined is there. How many m-dimensional cuts you can find such that the connectedness of m plus one dimensional space is not lost. So that's Beatty number. These are some kind of invariants. And then we had this invariance that could have some, that could give you some notion of okay, the what algebraic characters we have in spaces. But then what happened is that, after that, what happens is that, we can, it was shown by Leray. Leray is a mathematician who worked on this stuff when he was in a concentration camp. So what he did is that he took all those topological invariants and just construct something called sheaf over a space. You just take those invariants takes values in that sheaf. And then while define then Leray defined something called sheaf for the first time. Then what the sheaf does is that it takes all the invariants, takes values in that sheaf, and then when just this idea gives you a complete characterization of the space, algebraic characterization of the space. And while we can talk about this discrete stuff, so that's what where you can have that. So if you consider the set of all shapes, like for example, sheaves are, remember, sheaves are those things. For now, at least, sheaves are those things that takes those topological values of the those invariants takes values in that sheaf. So that is our sheaf of space. So when you take all such sheaves, and it turns out that all such sheaves, okay, we'll discuss what category is. All such sheaves forms a category of sheaves. So this category of shapes, it turns out that this category of shapes recovers the algebraic structure of the topological space. So what is category? A category is just nothing but a set of objects and transformation between objects. It's just transformation. We call it morphism. It can be function, it can be map, it can be in set relations, it can be matrix, it can be anything. We don't talk about in category theory, we don't talk about the nature of the transformation. It is only how the transformations are related to each other. So you have like different kinds of morphisms and different properties. That those properties give you the it satisfies specific constraints on the transformation. The the thing that's common is that we have a composition rule for the category, and the category is closed under the composition rule as given by A. And one more thing is that for every object there exists an identity morphism that takes that object to itself, and we of course have associated. So this is our category. And so if you consider this category of sheaves, then it turns out that the category of sheaf will be exactly retains the algebraic structure of the topological spaces, as you know, Grothendieck says here. So this when we take the particular notion of space, that using the help of category of space, category of sheets, we take the particular notion of space which was continuous, which we had only the valuation, we had only the ideas of size, shape, and all that thing, and then you gave it an algebraic structure. Then this algebraic structure is given using the category of sheet. So we can talk about the algebra. We can talk about different algebra without going into the topological space. We can just deal with category of spaces, which contains the nice topological properties of spaces plus the algebra of spaces. So the fundamental idea is that what Gurkhandek said that okay, so the main important things are not points or subsets of points or states. It's the sheets on that space that matters and the category which they form. So yeah, so basically a category will define as a paired ordered pair composed of objects and transformation. The transformations are basically morphisms. We call it homomorphisms because you know, we call it homomorphisms. So yeah, so that's okay. I so these are the like intuition of me and me blabbering in the background while you have time to read the whole thing. So yeah, so now I will go to the main part of the topic, which is the shift theoretical, which is the contextuality scenario, the paper itself. So we have two things. First is the event space, and second is the probability space. In the event space is where the actual observation is happening, and the probability space or the behavior space is where you collect the data, you construct your data table, you construct the probability. The main intuition, the thing in the category in shift theory, what it does is that the scenario or the event space is a category, and the behavior is another category. So when you have two categories, you can define a map between categories such that it preserves the composition rules. These maps are called functors. So what is functors? Functors is defined here. So you give two categories, and C and D, and capital F from C to D is a functor. If for every object and morphism from C, there exists an object and morphism in D such that you have the preservation of identity and the composition rule for the category is also preserved. So you see, this is a structure preserving maps. So when you have one category, which is for us, one category is scenario and another category is behavior. So from scenario to behavior, we need a functor. If we want some structure, we'll see that the distribution function or the measurement, these all satisfies these functorial properties. And so we can say that these are structure preserving maps. So yeah, so that's the whole of category theory we need right now. And so then now we'll go to the event algebra. So the scenario space or the event space or the category of events or the category of categories of events. So yeah, anyway. So what is event algebra? So you know this. So you have our standard. We'll consider the Alice and Bob for our purpose with space-like separation between them, but it becomes more general idea. So you have Alice, Alice's input A, Bob's input B, Alice output X, Bob output 1, Y, and then we define a particular event is just a map from an input to output set. And where my input set is a set of the context with compatible measurements. So compatible measurements for us is just reflexive binary, symmetric binary relationship with outcome X. Sorry, reflex symmetric binary relationship with outcome. Sorry, reflexive symmetric binary relationship. Not, I forgot the bracket here. So yeah, so this is my event, and the all such events given a particular input which is u, all such events is a measurement of u. So this maps to this O of u. So this takes an input space u and maps to O of u, and each outcome of that event, that is S, is a element of that O of outcome of u. So this is basically a power set of u, but yeah, we don't need that much detail for now. So now we see that what we have is that in input, for example, Alice, consider a input, a context u, and now consider another subcontext u prime. And the idea is that any measurement of u induces a measurement in u prime. And how does this how does measurement in u induces a measurement in u prime? You can take a measurement in u, you remove the outputs which are not in u prime. So for example, uh, in here you can just consider AB equal to AB and A prime B, and AB 00 and A prime B 00, then B0B is the, like, 0B is the U prime in here. So this this discarding map we can formally define it. So in terms of what we call restriction map. So it restricts the large set U to a smaller set U prime in such a way that all the outputs, all the elements of OU maps to the elements of OU prime, where we just remove the outputs which are not in U prime from the elements of OU. So this is, we can formally define restriction map on the output set like this. So now we have two categories. One is the input category where you have input sets and the set inclusion maps, and we have the output set with the restriction maps. So these are, you could you could show that this satisfies those properties of categories, but I'm not proving that. The idea is that so now you have a map from the input category to, okay, let's call this output category. So from a map from input category to output category, which is this measurement map E. The claim is that this E is a functor in the sense that it satisfies this preservation of identity and preservation of the composition rule. So how do we show that? So the first one is easy. Suppose restriction of U in U is identity, because it will give you the entire U. And the second one, like for the second one, you can see that this is my composition law for the inclusion map. Like when U prime is a subset, U double prime is a subset of U prime, and U prime is a subset of U, that implies that U double prime is a subset of U. So this is my composition law that I have seen there, and we can show that this composition law holds in the restriction map also, as given is given in this commutating diagram. These diagrams are called commutating diagrams, but as given in this diagram, we could show that, okay, this, we have the composition law for the input category above, and this works. Okay.
Shomda,
Mhm.
just one question I might have missed. What is the U double prime and U prime?
Oh, these are all subsets. This is
Oh, okay, okay. I mean arbitrary subsets like U.
arbitrary subsets of U. U is the context. For us, U is the
Okay, okay,
context
okay,
with computable measurements.
okay.
We
Thank you.
haven't imposed what compatibility structure, so you can take it as arbitrary compatibility structures for now. Okay.
Okay,
So,
okay, okay. Thank you, thank you.
okay. So now we have this. Now you can see that this is basically our functorial relationship. Okay. This is basically our functorial relationship here. So this I can write it just as U prime to U double prime to U implies U to double prime. Something like this we can write here is the closeness of the inclusion. We have the inclusion maps here. And so we also have the, yeah, inclusion map here. And similarly, you can see that the restriction map. So what does this restriction map does here is that you apply the measurement of U, you get the whole set of outcomes here, and then you restrict any outcome from OU in such a way you restrict to U prime. So all such outcomes OU prime you can obtain by restricting the S to U prime. So this again will give you measurement of EU prime, and similarly you could have the, for the EU double prime also you can restrict EU prime to further U double prime by removing suitable elements, and you get the whole outcome space of OU double prime. So yeah, so you see that like this satisfies the composition rule. So yeah, so these two properties are called functorial properties. So when it satisfies these two properties, we say that it preserves the structure. One more interesting property that it satisfies is called pre-sheaf property. So pre-sheaf property is what? Consider two subsets, U and V, with a non-empty intersection. So the events of that non-empty intersection discarded, can be obtained by discarding the outputs which are not in that intersection from suitable institution events of U or V. And this is what is given in the second part here. So you have, you could see that like V and U both contains the intersection as a subset, and then you have the maps there, you have the measurement maps that is a map to the output set, and similarly you have the, and any element on OU is S subscript U, any element on OV is S subscript V. Now, any element in the intersection you can obtain either by restricting the elements of the outcome of U or restricting the outcomes of V, and it will give the entire outcome space of the intersection. So, this property is called pre-sheaf property. They agree on the overlap. If the pre-sheaf property is satisfied for all the overlaps, then it is called a sheaf. So we would see that. So this basically means that, okay, I'll explain the physical intuition of the sheaf property in the next slide. So what happens is that define our scenario in the we'll define what our scenario is now properly without, so suppose we have a input set X and we have a set of subsets. which are called context for us. And each element of MI, the elements within MI are compatible. And we want the particular property called union of all the contexts returns you the entire input set that says you cover. And we have one more property that no two contexts have uh, two contexts cannot be the subset of one another. They have non-zero intersection, but they can have finite intersections, but they cannot contain one completely within. So this set of contexts is known as maximal compatibility maximal compatible families. Yeah. So I'll define they also I'll just say this as the measurement cover. That's the word that Abramsky they used. So now consider section or event for MI is SI. And now we consider okay, suppose there is a set of events which agrees on all the overlaps. That means that suppose you take two events, SI and SJ, you restrict both the events to the common common subset and it agrees there, and this happens for all the common subsets. So this is this particular compatibility. So this is a kind of compatibility in the overlaps. So this kind of compatibility is known as the Sheaf compatibility relation. And in the paper Abramsky Brandenberger, they have shown that okay, for a fixed quantum state, if you have commuting measurements, like sequential commuting measurements, they then they then the statistics satisfy the Sheaf compatibility structure. So when they satisfy this Sheaf compatibility constant in the sense that if they are consistent, they agrees on all the overlaps, like, or all the non-zero, no, all the finite intersections. Then we have a unique global event that is S from X to O, which X is the set of input state, such that if you from that global event, if you start restricting your if you start restricting to ith context or jth context, then you will you'll exactly achieve the statistics of the i's context and j's context, and you will also achieve the exact statistics of the common subcontext, which is the intersection between the two contexts. So when so this so you remember the pre-shift condition that I told you, like if the pre-shift condition is that it's at the shape, the input to output, it has your it agrees on the overlap, and if it agrees on the all the overlaps, like it happens for this cover here, then we have a unique global section which are consistent on the overlaps, and that this converts the pre-sheaf of functor or event to a sheaf of events. So mm, this this idea would be this compatibility. This is the general compatibility structure that Abramsky and Brandenberger they have used. So yeah, and they say that okay, this compatibility structure, when your contexts are space-like separated parties, this sheaf compatibility behaves as no signaling. When your context or sorry covers are orthonormal families of orthonormal bases in d-dimensional Hilbert space, you can have a Kochen-Specker kind of argument from the sheaf compatibility structure. given time. So in that sense, the Sheaf compatibility combines both the no signaling behaviors of the bell and the Cochen-Specker type non-contextuality behaviors. So yeah, if we have time, we'll go through we'll show one example of how they do that. But for now, what we just say that okay, pre-sheaf satisfying. We'll just say that okay, if you have pre-sheaf, the pre-sheaf is that when the data agree on the overlap, and pre-sheaf becomes a sheaf when the data or the events, sorry, events agree on the overlap, and pre-sheaf becomes a sheaf when events agree on all the overlaps. So this is my structure, algebraic structure of the scenario space. Now we'll go to the probability space, which is our observational data or the statistics. For now, before here we didn't perform. We just had the abstract idea of how an experiment is performed. Now we collected data and we have a probability table or vectors or the polytope with deterministic vertices, all that thing. So we'll see. So where we map the objects and the transformations of the event space to the objects and the transformation of the probability space. So again, we have the functor reality relationship. It will play a role there. We'll see how. So we have a behavior. So remember, we define our scenario as input, cover, and output set. And so the probability distributions of the our behavior is a probability distribution over the outcome space. We have with a finite support, and it has with a finite support, and each probability we have a probability distribution for each context u in the cover. The curious part is that the d subscript u, which is the number, it can take values in real field or non-negative real field or Boolean field. Usual probability we take as non-negative real field, but you can when you take it to real field, it corresponds to negative probability, and when you consider Boolean field, it corresponds to true false assignment. So we won't have time to go through all these three separate behaviors. We'll take on for now. We'll take only a Boolean field, which is d. You can take 0 and 1 most of the time. We'll take that. So now, in general, this field we call it a commutative semi-ring in the sense that it has operations like addition and multiplication, and it has elements like 0 and 1. So yeah, so we call it a commutative semi-ring. Not important for our purpose, but yeah. So what happens is that when you we have an event and we have an observation for context u, and then when you take the data of that observation, so what you do is that you take the out elements from the output space and map it to the R, which is our semi-ring R. And when you map it to the R, it gives you a behavior which forms a polytope with certain number of deterministic vertices. And then, so when we have a polytope with a deterministic vertex, then for a context U, suppose it has Cj number of elements in that context, which are again members of the input set. The elements of OU, you can just say that, okay, these are strings with M elements. So, yeah, so if it is true false, it will be like to the, it will be like M bit string. If it's three outcome scenarios, it will be like M trait string, and in general, it will be like M dit string. So, yeah. So That's our behavior, vector for the behavior. Now you could see that how the restriction maps, what, how do you, what's the bearing of this restriction map? We have this restriction map here. Uh, how does this restriction map constrains the vectors in the behaviors? So what? So we can take any subset of the context U, and then again you remember that outputs of U are the m element string, and a subset of U again would be like out of these m elements, you remove some elements and keep only those elements which belongs to C. So you can just define your restriction map as this: from any restrict U to C is like you take a S, this is outcome from the set of from OU, from the outcome set of U, and then you restrict S in C by only keeping those outcomes which are in C and removing the rest. So this is our restriction map in the events. How it behaves in the probability space or the behavior space is given in the following. So you have a distribution for U, which is BU. You restrict the distribution of U at C, uh, capital C. Suppose small c is an element of capital C, and you want to restrict the behavior, the outcomes of U in such a way that the context, the outcome of the context capital C is small c. So this is the left hand side of, this is what this denotes. This is, you can say this is a marginal distribution of, this is the marginal distribution of C from the measurement of U. This is what it means. So, so now what happens is that when you restrict the distribution du at the subcontext C, that will only pick up elements from the overall output S, like your, the complete output S from OU, and from S you will pick only those S. If you this restrict the S to the context of C, and you will get capital C and you will get small c here. So you will only consider the sum over only those S on the complete, on the outcome category of, on the outcome space of U, in such a way that when you restrict those outcomes to capital C, it will give you small c. So this is the marginal distribution of small c when you have a measurement outcome, when you have a measurement of U. So this also, so you see that this also, like the restriction map in the probability space, you have the marginal distribution here. So restriction map, the probability space, it captures the idea of marginal distribution. So one can just proceed the previous arguments and show that the distribution and the restriction, it satisfies the functorial properties in the sense that, the restriction, this would follow. So what we have is that we have this. Right? Okay, I'll just wait. This is my restriction map from G to G. Then you have, you can just restrict. So suppose like, right, okay, that's right, x to y to z. That's much better. X to y to z. We have f of g, and then you can just write duz equals to sum over x such that g of f of x equal to z. This is okay. I like probability of it. This is the conditional du of x. Yeah. So this shows that it follows. It satisfies the functorial properties. So yeah. So that's what we have here. So we also show that okay, distribution satisfies the functorial properties. But what does this mean? We have a functor of events in the event space, and we have a functor in the distribution space. So the idea the idea is that you remember we talked about the sheaf compatibility condition, right? So as sheaf was here when we had overlaps between pre-sheaf when they agree on the overlaps, it's a pre-sheaf. When it's agree on all the overlaps, it's a sheaf. So as we shown, uh, as we showed before, the pre-sheaf or a functor of event is a sheaf in the sense that it agrees on all the overlaps. Now the question is, does the distribution functor agrees on all the overlaps? What does that mean? Agreeing on all the overlaps for the distribution function. So yeah, so we have a scenario which is a triple input say context cover, which is covers are created using UI and output set with a set of distributions BI, and it forms a sheaf if there exists a global event S in the output set of the entire input set, and it and the associated distribution D such that you restrict it to each context and get the correct marginal, and also it will agree on the overlaps. Like the marginal distributions of the overlaps are also same. So you see that this is what no signaling condition is about when your covers are space like separated parties, or as I said before, a Kochen-Specker's assignment when the covers are families of orthonormal bases in d-dimensional Hilbert space. So yeah, so what Fine Abramsky Brandenberger they actually did is that, okay, this if you have a global event, then you have a deterministic distribution or deterministic hidden variable that's defined over all the measurements, and it will give the correct statistical data which are independent of the context. So if you have a global section, it has a non-contextual assignment or local assignment. The other way around is also true, that if you have a non-contextual or local assignment, then you have a global section or a global deterministic event. So I'll just briefly go through one part of the proof. The other part, I don't have time. So the other part is not, the other part is a bit complicated and I don't quite understand it yet. So what happens is that if you have a deterministic, if you have a global section S in OX, then you can just define a deterministic hidden variable here, deterministic distribution like this, and then then you can just use the idea of restriction map, which removes the elements, removes the irrelevant elements from the outcomes, and you could just show that the, it is factorized for each context. The distribution in each context is factorized, and you can get the correct context from the correct statistical data from the from coarse graining or averaging over the deterministic distribution function. So what Fine-Abramsky proof is that a global section for an empirical model exists if and only if it has a local or non-contextual hidden variable model. If there is no global section for a set of behaviors, then it constitutes a test of non-locality or similarly a Cochen-Specker contextual. So it means shown that the existence of global sections is just a linear program, and yeah, there have been works on this, but I'll explain another way to that was again mentioned in this paper by Abramsky and Hardy, which is the same thing, just in a bit more easier way. So obstruction, basically the obstruction of global section implies that okay, all the context, like all the propositions all for a context, you define some proposition, some probability, some random variables. And obstruction of global event happens if for each context you define a random variable and the random variable takes a value that's 0, 1, 2, something. And the obstruction happens that the values, each all the random variables cannot take the desired values simultaneously. In the sense that each random variable defines a proposition, and all the all the propositions cannot be simultaneously satisfiable. Then we have this particular inequality if the n number of propositions does not satisfy uh, n number of propositions are not simultaneously satisfied. So it turns out that the polytope of the non-contextual probability model over any arbitrary cover. So any arbitrary cover would imply that arbitrary compatibility structures which we have in the which gives rise to no signaling or Cotten-Specker cases. Okay, so this the polytope of the non-contextual probability models over any arbitrary compatibility structures is determined by a finite set of logical Bayes inequalities. And these inequalities can also be you can get from them. I'll give some examples here. Uh, for example, this probability table. Consider this time. This thing is just probability of A equal to B equal to 1. And this gives you probability of A equal to B prime equal to what? 384. This is also the same. Like you add this and this, you will get 34. And you'll add this and this, you will again get 34. But you see that this is like A prime not equals to B prime. And this is A prime equal to B. Now you see that these, and these propositions are not simultaneously satisfiable. So the sum will be less than equal to 3. But here the sum is like 34 into 3 plus 1, that is 9 by 4 plus 1, that is 3 point something. Yeah. So you see that this probability table violates the logical Bell inequality. In fact, this is one of the CHFH table. So now, but here one thing is that we assign the specific probabilities here. Like this is a specific behavior here. So now we can. ask that, okay, can you go beyond a particular behavior? So suppose, can you say that, okay, there is a class of behavior. This class of behavior is non-contextual. So can you do that? So that would say that, okay, so this can be done, like this is a table for the Hardy. So you can see that this table is constructed from the data table in such a way that if probabilities are non-zero, then we assign one. If probabilities are zero, then we assign zero. So this is called a support table. So what we have is that, this support, you could see that in this support table there exists a subset for which there exists no global section. That subset is given by here, like the 1, 2, 3, 4. So yeah. So how do we see this? So this is easily, you can see this. So you can see that negation of A. So for example here, uh, okay. For example, last consider the last proposition, A prime or B prime. A prime or B prime, it means either A prime is true or B prime is true. So that would mean that this is where A prime is true, this is where B prime is true, and this, or both is true, but this we ignore. So only these two values. And similarly, we have negation of A prime and B prime. Like that would mean that both A prime and B cannot be true. So yeah, you could see that like both A prime and B prime cannot be true. Suppose I take 1 as true and 0 as false, then this will be there. Similar. So only these two, and similarly this would be this here. So only these two. So and these three essentially means that, A prime, like A or B, not won't happen, because your this would mean that A not equal to B prime, and this would be not equal to B prime. This would mean that A prime not equal to B. This would mean that A prime not equal to B. And these three simultaneously means that A cannot be equal to B. So that means that A and B is not. So what happens is that, so this is my Hardy table here, and what it shows that for any non-zero value of the proposition A and B, you have a contradiction with the model. So contradiction with the non-contextual assignment. So this is what they call possibilistic contextuality. So the the general idea is as follows. So suppose you have a context, you have measurement over the context, you have the measurement result. You can define a proposition phi I, which has a set of satisfying assignments in the OU, that is my output space, and the output space is for now 0, 1. And if for each context, if we assume our phi I to be a formula which satisfies the proposition that has non-zero supports in the non-zero supports, that is my S of UI, then global sections are like the when all the propositions are simultaneously satisfied. It has a global section if and only if all the propositions are simultaneously satisfied. It does not have a global section if and if there is no there does not exist such a global proposition. So as we looked at in the Bell case, we modeled a particular behavior. Where in the Hardy case, we didn't model a particular behavior, we only took the data of the support, and then we show that the a subset of the support does not have a global section. Now, what would happen if the entire support does not have a global section? That kind of cases happens for PR box and CSA. Then we call it a strong contextuality. So we have two different contextuality. One is probabilistic contextuality that shows the contextuality for a behavior. We have possibilistic contextuality that shows a contextuality for a class of behavior from the support. And the possibilities is that, okay, within the support, there exists a set of events for which there does not exist a global section. But for the strong contextuality, the entire support does not have a glo- global section. So it has, like, go, you could model, you could show that, okay, in this sense, like Bell, the contextuality of Bell is weaker than the contextuality in hard D, and it is simultaneously hard D contextuality is weaker than the ZZ contextuality. And there are works on the in terms of contextuality monotones that shows that. And previously, I think in 1996, Cabello also showed something similar from case colorable sets, so the existence of case colorable sets. So finally, okay, so I'll show the, I'll see how the Cochin Specker, like the 18 vector proof of Cabello comes about. So these ABCDs are bases in R4, different bases. So we need maximal competition, and since we have the dichotomic structures and these are all pure states, and when you perform each measurement, you can pick one of the measurements from the 9 measurements, you can perform one measurement, then only, like, for example, you perform the measurement one, then only one of them, you can detect only one of them, like either this would be one, or this would be all zero, or this would be zero, this would be all one, B would be one, and this all would be zero, or again, or this would be one, rest would be zero, C would be one, rest would be zero, or D would be one, rest would be zero. So when you perform a measurement, only one of the one of the values you can assign one, and rest of them is zero. So this is a proposition for a single E. Now you could see that, okay, if you construct something like this, uh, then this is false for this particular assignment. So then here we have a global section. We do not have a global section for this particular assignment. So yes, so this is what the Cochin speaker has done. And okay, there are future work. There are some work that they have been done. For example, resource theory of contextuality, and they have defined some contextual fractions as monotones, and then they are nowadays they are also discussing these compatibility structures beyond no signaling to signaling structures to arbitrary causal structures. And yeah, we also have a operational meaning to the negative probability that they have. This is just what they say is that this is just a standard probability measure with some kind of signed or phased events. So you have some kind of signed events. So that's there are people who have been doing lots of stuff in there. So yeah, that's all. So, thanks. Yeah.
Thank you, Som, for your talk. If you have any questions, please ask. Okay, maybe there is no question.
I have no, I have a question. Hello, can you hear me?
Hello,
Yeah,
but noise is coming. We can't hear you.
Oh, okay, okay. Can you hear me now?
we can hear and
Still no, actually. We can hear you.
Okay.
Yes, you can ask your question. Anything.
Yes, yes, yes. Thank you, Shom, for this talk. So I'm completely new in this, and there are lots of new concepts also. So I have, so you have here defined that. So there is the event space and there is the behavior space, right? And you have some filter which connects the event space to the behavior space. And you have
Mhm.
only talked about like no signaling kind of scenarios that you
Mhm.
can define as like space-like events, and also here no signaling correlations. So I was wondering whether it is also possible to like generalize for other causal models, or for example, like the causal inference problem. So could it be framed in the Sheaf theoretic framework?
Yeah, so first of all, they talk about arbitrary incompatibility structure in the
Mhm.
behavior. And then they showed that, okay, so when we say arbitrary, it means that it satisfies the pre-shift condition, that, agrees on some of the overlaps. But when you have the shift condition, it agrees on all the overlaps, right? Then it is similar to no signaling when you have the space-like separated parties there. For causal structures, they have some works here, like where they discuss, like they have a definite causal structure, like they do not consider, you know, the causally non-separable process. They consider that, okay, like these two papers, and there is a couple of more. They discuss that, okay, so you have these causal structures here. So how would you, like, what does it mean by existence of
Okay.
global fusion and that?
Okay, 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 okay.
They discuss these things.
So it
But
asks, it,
okay, one more thing I would comment before. In principle, it is possible to go to, okay, when you say arbitrary causal structure, I could also include prepare and measure tasks, right? Like, for example, sequential scenarios, right? So, in the case of sequential scenarios, like as like we have this approach that I haven't talked about here, is that you do in the compatibility graph, exclusivity graph approach, which basically which uses like this Sheaf theoretic argument, but just in a graph theoretic representation. So what they do, they study sequential situations or with sequential situations there. Like for example, CHSH there is model that like okay, Alice and Bob. Alice will measure first, Bob will measure second. So Alice has A1, A2, Bob has B1, B2. So Alice measures A1 first, Bob can then pass the system. Bob can measure either B1 or B2. Then you have the CHSH correlation. And then they discuss this, you know, this obstruction of, then you could essentially get the Bell thing for the sequence. It will be a Bell thing, the Bell scenario will convert to a cycle, four cycle scenario in that case. And they discuss this there. Similarly, any Bell scenario, I think some cycle gains. These are called these sequential gains are called cycle gains, in cycle gains.
okay. Yes, yes, yes. So that is what I was asking. Like, given some behavior, which kind of causal structures is it compatible with this kind of studies?
Hmm.
So this they do in this work, you are saying.
Yeah, but that given a behavior, I don't think like this particular question they have they have not addressed like given a behavior what particular causal structure it satisfies. In this, they have, or whether you find a causal structure, a particular causal structure that satisfies that behavior, right?
Yes,
This
yes,
is
yes,
the
yes.
motivation. So here, like in these two paper, like this is the first paper is like Abramsky, Emisol and Rui. This is one paper, and we have this Gogisopigiani paper who wrote like they have some three papers. Each paper is like 50, 60 pages long, where they
Yes, yes,
discuss
yes.
the causality in this framework. How would you extract the correct causal structure? But we also have the inflation technique for that. No.
Right, right.
Yes.
Thanks.
Okay, let's hold your questions for future. Let's thank the speaker again, and we will end here today. Thank you, Som. Bye.